For our first review section, we'll talk about limits. So back in our Introduction to Limits section, here's some stuff that we learned. We learned that limits don't necessarily mean that the function exists. In these three examples, this one, the function exists and the limit equals what the function equals. Remember, later on we learned that that's called continuous. In this one, the limit still exists. The limit from the left of 1 and the limit from the right of 1 both go to 2, but the function does not exist. Notice there's an open hole there. So this function is not continuous. We call that a removable discontinuity, which again we learned later. But the limit still exists. From the left and right it goes to 2, even if the function does not equal that. And then for this one, the limit exists, the function exists, but they're not equal to each other. The function is equal to 1, the limit is equal to 2, therefore this is not continuous, again, because it has a removable discontinuity. We talked about, in order for a limit to exist, that the left and right-hand limits must be equal to each other. So for this one, the limit from the left is equal to 1, the limit from the right is equal to, the limit from the left of 1 is equal to 2, the limit from the right of 1 is equal to 3, therefore the limit does not exist since the left and right-hand limits are not equal to each other. And so we wrote it like this, down here at the bottom in red. The left and right-hand limits need to be equal to each other in order for the limit to exist. After that, we briefly talked about infinite limits graphically. So you can see both of these. These are limits going to infinity. So notice this is the limit as x goes to positive infinity. Here we have the limit as x goes to negative infinity. In those cases, we consider the end behavior of the graph. So what's happening at the ends of the graph. In this example, we're talking about a horizontal asymptote. So the limit over here as we go towards positive infinity reaches 2 because the y value is 2. And the limit on this side as we go towards negative infinity is going towards 0 since there's a horizontal asymptote at 0. Then we went on a little bit further, we did some examples. And then we talked about the other kind of infinite limit, not necessarily a limit going to infinity, but this time a limit equaling infinity. So this is when we talk about vertical asymptotes. So the limit as x approaches some value from the left and the right might go up to infinity or down to infinity. So in this example, as we approach a from the left, we're going to negative infinity. As we approach a from the right, we're going to positive infinity. So vertical asymptotes are when we have limits equaling infinity. Horizontal asymptotes are when we have limits that approach infinity as x goes to infinity. After that, we went on to talking about limits algebraically and how to solve limits algebraically after we talked about the graphical component of it. For the first method we talked about direct substitution, where you literally just take a value and plug it into the function. So for this one, if we take 3 and plug it into the function, we're actually going to get a number out of that. For this one, we plug 2 into the function, you're actually going to get a number out of that. Direct substitution is by far the easiest type of evaluation, but does not always work. The next type we talked about was piecewise functions. We said for piecewise functions that we need to evaluate the limit from the left and right-hand side of the piecewise function. So for example, you can see in this piecewise function, it's broken up around the value at -2. So if we're evaluating a limit at -4, we only use the piece where x is less than -2. So we would have just plugged -4 into this first part right here, since -4 is less than -2. If we're evaluating a limit at 0, we would choose the second piece. Since 0 is greater than -2, we would just evaluate this second half of the piecewise function at 0. However, when we're trying to evaluate a limit of the piecewise function at the point where it breaks, where it's changing its function, we need to approach the limit from the left and right. So we would plug -2 into the top function to get -10, but we would also plug -2 into the bottom function. -2 cubed is -8, -8 minus 2 is also -10. So since the left and right-hand limits are in fact equal to each other, we would say the limit does exist and the limit as x approaches -2 is -10. That's not always the case. Sometimes the limits are not equal to each other. If the limit from the left and right are not equal to each other, we would just say the limit does not exist. Taking it one step further means that that's not continuous. That function is not continuous. The next way we learned how to evaluate limits was by factoring and dividing out a common factor. For example, this one, we learned later that we can also use L'Hopital's rule, but the first way we learned how to do this one was by factoring and simplifying out the common factors. So if you factored x squared minus 2x minus 8, you would have gotten x minus 4x plus 2. And if you factor out the denominator, we get x plus 2x minus 2. And since we have that common factor at x plus 2, we could simplify it out by dividing it out. and then we can reevaluate by direct substitution and plug -2 back into the function again. So that was one of the ways. But L'Hopital's rule does work for that as well, since when you plug in -2 at the beginning, you get 0 over 0, which is the indeterminate form. And here we talked about the indeterminate form. So this was kind of our preface back then, talking about how we would eventually learn L'Hopital's rule. We also learned how to evaluate limits by rationalizing the numerator or the denominator. So in a case like this, we were going to multiply by the conjugate. So you can multiply by the square root of 5x plus 4 plus 3 on the top by switching that sign of -3 to a +3. And you also want to multiply by that on the bottom, 5x plus 4 plus 3. By doing that, you create a difference of 2 squares on the top, which allows you to get rid of the whole. You'll eventually multiply that out, and the whole will divide out to be 1, just like in factoring. So this is one method, but again, L'Hopital's rule would have worked here as well. If we plug in 1 to the numerator, we're going to get 0. If we plug in 1 to the denominator, we're going to get 0. So you could have also done this problem by using L'Hopital's rule. So one way to do it is by rationalization. The other way to do it is with L'Hopital's rule. Another strategy we learned was rewriting our problem using trig identities. So for example, here using the double angle identity, we could have rewritten this. In this example, we are able to use L'Hopital's rule as well, since when we plug pi over 4 in, we get 2 times pi over 4, which is pi over 2, and cosine of pi over 2 is 0. And then on the bottom, cosine of pi over 4 minus sine over pi over 4 is also 0. So we could have used L'Hopital's rule for this as well. Probably the way I would have leaned in all these examples is to use L'Hopital's rule, just because I only have to remember one rule as opposed to a bunch of different ways of simplifying, but that's totally up to you. If you want to use these different identities to simplify, you can do that as well. Moving on to limits at infinity or limits involving infinity algebraically. Remember that anytime a limit as x approaches infinity, we're talking about a horizontal asymptote. So if we're talking about a horizontal asymptote, we can look for the degree of the numerator and the degree of the denominator. Since the numerator is smaller than the denominator, that means that we have a horizontal asymptote at 0. So therefore, we would be approaching 0. For a limit as x approaches infinity. L'Hopital's rule also works here, however. If you plug in infinity, you're going to get infinity over infinity, and that simplifies to 0 eventually after a few rounds of L'Hopital's rule as well. This is an example that comes up every once in a while as well. Limit as x approaches infinity. In the numerator, we would get the square root of x squared, which as we approach infinity essentially becomes or follows the end behavior of what would happen if you actually square rooted x squared, which is x. It would follow the end behavior of x, since the square root of x squared is x. On the denominator, we have 2x, so since we have the numerator and denominator with the same degrees, they both have an exponent of 1, then our limit as x approaches infinity would be the ratio of the leading coefficients. So on the top, we have 1, on the bottom, we have 2, therefore there's a horizontal asymptote at 1/2. The other type of limit involving infinity is when we get an infinite limit as an answer. So the limit as x approaches 2. Notice if we substitute 2 into this function, we get 2 times 2 is 4, 4 plus 5 is 9. On the bottom, 2 minus 2 is 0. So we get 9 over 0. Anytime that happens, that is not the indeterminate form. That is an infinite limit, meaning that the function is going to follow an asymptote, a vertical asymptote. So this is the one where we evaluate from the left and right. So we could plug in a number really close to 2 from the left, like 1.9. If I plug 1.9 into the numerator, I'm going to get a positive number. If I plug it into the denominator, I'm going to get a negative number. So a positive divided by a negative is a negative. Therefore, the limit from the left would be approaching negative infinity. On the right-hand side, if I plug in a number a little bit more than 2, like 2.1, we would get a positive on the top and a positive on the bottom. Therefore, from the right-hand side, the limit would be approaching positive infinity. Therefore, we have a vertical asymptote with the left and right-hand limits going in opposite directions. So our limit does not exist, since one goes up and one goes down. The next lesson we talked about was continuity. So we talked about how an example like this is called continuous. This is removable discontinuity, and this is also a removable discontinuity. These were jump discontinuities. So the limit from the left and right are not equal to each other. There's a significant jump in the graph. We have an infinite discontinuity with a vertical asymptote, and then an oscillating discontinuity because the graph just keeps going up and down, up and down, up and down forever. We talked about the definition of continuity, that in order for a function to be continuous at a point, the limit needs to exist at that point, the function needs to exist at that point, and the limit and the function need to be equal to each other at that point. And our layman's term definition of continuity was that if you can draw the entire function without ever taking your pencil off the paper, then that function is continuous. Oftentimes we're asked to analyze continuity as a breaking point, so we talked a little bit about this earlier. If we're going to look at the limit as x approaches 1 from the right-hand side, plugging 1 into this first function, we get 1 squared minus 3. Well, 1 squared is 1, 1 minus 3 is negative 2. If I plug 1 into this function from the left-hand side, we get 1 minus 1 is 0. So since the top part of the function, the limit from the right was equal to negative 2, and the bottom was equal to 0, since the left and right-hand limits are not equal to each other, we would say the function is not continuous. We also talked about removing discontinuities, so instead of asking whether or not this function is continuous, they are asking us to force it to be continuous, so finding a value for k that would force these two functions to be continuous. In order to do that, we would essentially evaluate the limit from the left and the right, but make them equal to each other. So if I evaluate the limit from the right, plugging 1 into the first function, we get 3 times 1, which is 3, plus 2, which is 5. In the bottom function, if I plug in x for 1, I get 2 times k minus 1. And I want the left and right hand limits to be equal to each other, so I would just set those equal to each other and then solve for the k value that made that true. So add the 1 over and divide by 2. And the last thing we talked about in this unit was the intermediate value theorem. We said that if a function has two endpoints, a and b, whatever their y values are, f of a and f of b, the intermediate value theorem essentially says that for all the points in between a and b on the x-axis, whatever their corresponding y values are, they have to attain every y value in between f of a and f of b. So every single one of these y values is going to be attained as long as this original function was continuous. That's what the intermediate value theorem says. There's lots of different applications of this and ways that it's applied on the AP test, but that's the general overarching concept for intermediate value theorem. All right, at this time we're going to go over to our review, and I'm going to do a few questions from the review. So the first one that came from this section, I hope I saw them all, or got them all, I should say, was number 6. This is an example of evaluating a limit algebraically. When you plug negative 3 into the function, you may find that it equals 0 over 0. So since it's in the indeterminate form, you can use L'Hopital's rule. But I'm going to go back and do it the way that we learned it originally, which was to factor and simplify out the whole. So if I factor the numerator, I get x plus 3, x minus 3. If I factor the denominator, I get x minus 5, x plus 3. So since I have this x plus 3 factor in the top and bottom, in the numerator and denominator, I can simplify that to be 1. And if I reevaluate by direct substitution, I can plug negative 3 into the numerator to get negative 3 minus 3 is negative 6. I can plug negative 3 into the denominator to get negative 3 minus 5, which is negative 8. And then if you simplify negative 6 over negative 8, you get 3/4. So answer choice C. The next one we'll look at that deals with limits is 18. For number 18, we have this graph, and it asks us which of the following statements are true. So the first one, the limit as x approaches 2 from the left is equal to f of 2. So here's x equals 2. The limit from the left comes in this way. So the limit from the left is coming into negative 1. And then the function, see how it has a closed circle here? So the limit from the left is negative 1, and since there's a closed circle, the function itself is also equal to negative 1. So yes, that's a true statement. For the second part, the limit as x approaches 6 from the left and from the right are equal to each other. All right, well here's 6. The limit from the left of 6 approaches negative 1. The limit from the right of 6 also approaches negative 1. So yes, those are in fact equal to each other. The function doesn't equal negative 1. The function equals negative 3, but the limits from the left and right are equal. And last but not least, the third one says the limit as x approaches 6 is equal to what the function is equal to at 6. So no, we just talked about how that's not true. The limit at 6 is negative 1, but the function at 6 is negative 3. Therefore, that part is not true. So the only parts that are true are 1 and 2, answer choice C. So the function is not continuous here. Just to add on a few other things that we've talked about, this is a jump discontinuity. At 2, we have a jump discontinuity. At 6, we have a removable discontinuity, since I just have to move one point in order to make it continuous. Number 19. Number 19 kind of got cut off a little bit. I think this was supposed to be a 2 up here. It says, let f be the function defined above for which of the following, or for what value of b is the function continuous. So again, they're asking to force it to be continuous. They want it to be continuous. So notice that we have this point. We have a point at 2 comma b, which means probably that there's going to be a hole in the graph. Because if there's a hole in the graph and I want this point to fill in that hole to make it continuous. So in order to figure out where there's a hole, I'm guessing x minus 2 is going to be a factor that we have in common on top and bottom. So let's go ahead and factor out the numerator and see if we have x minus 2 as a factor. If I factor it out, I get x minus 5, x minus 2. So yes, x minus 2 is a factor, all over b times x minus 2. So there is a hole in the graph at 2 because we have that factor in common on the top and bottom. So if we get rid of that hole, we can reevaluate the limit by direct substitution. So if I plug 2, which is where the hole is, if I plug 2 into this function, I get 2 minus 5, which is negative 3. Try to move this over a little bit. I get negative 3 over b. So that's what my limit is going to. And I want this y value to equal that limit. So I'll try to write it down here. I want this limit of negative 3b to be equal to wherever this point is. So I want that to be equal to b. So if I multiply the b over, I get negative 3 equals b squared. And then last but not least, to solve for b, I want to take the square root of both sides. So that means that b is equal to the square root plus or minus the square root of negative 3. Well, you can't take the square root of a negative number, or at least it's not a real number, so therefore the answer choice is E. There is no such value of b that would make this function continuous. Number 23. We have talked about number 23 in pretty serious depth at some point or another. In fact, we put it on like 2 or 3 of your quizzes. So let's just talk briefly about it one more time. Remember this function when we have the absolute value of an expression, and then we have that same expression in the denominator or vice versa. It ends up creating a graph that looks like this, centered around wherever that centered point is. So in this case, it's centered around 3. All right, so it creates that graph where on one direction it shoots off at positive 1, and then because of the absolute value in the other direction, it shoots off at negative 1. So they want to know what the limit as x approaches 3 from the left is. So as we're coming into the left of 3, from the left, we realize it's at negative 1. So the correct answer is B, the limit is negative 1. If they asked from the right, it would have been positive 1. And if they asked at 3 in general, it would have been does not exist, since the limit from the left and right are not equal to each other. Let's see if we have any more limit problems to do from this review guide. Those are all from the non-calculator section, by the way. And here's one from the calculator section. Number 8 in the calculator section, which doesn't actually require the use of a calculator, but sometimes they do that to us, where they put them in the calculator section. It says the vertical line x equals 2 is an asymptote for the graph of the function f. So if I just drew a rough sketch of x equals 2, it would look like this. It says which of the following must be false? This first one, the limit as x approaches 2 is equal to 0. Well, I can tell you right now that must be false because we have an asymptote at 2. Therefore, the limit does not exist. It's either going up to infinity or down to negative infinity. So I can tell you right now that's not a true statement. Let's just make sure we understand why the other ones could be true. The limit as x approaches 2 equals negative infinity. Sure, if both ends go down, that shows an example where the limit is equal to negative infinity. Part C, the limit as x approaches 2 equals positive infinity. Sure, if both ends had gone up instead of down, then we would have the limit equaling infinity. Part D, the limit as x approaches infinity equals 2. Sure, that's talking about a horizontal asymptote. Maybe as I go towards infinity, I have a horizontal asymptote at 2, at y equals 2. That's a possibility. I could totally have a horizontal asymptote at y equals 2. And last but not least, the limit as x approaches infinity equals infinity. That just means the graph could be unbounded, so it could go up forever as it approaches infinity. All of those are definite possibilities. The only one that could not be true is that our limit at 2 could not be 0. There's no way it could be 0 because of that asymptote. I think that was the last one for limits. So we'll go ahead and move on to that next section now.